It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Farming You a Nice Coffee. Hi guys, welcome to the next video. What I'm going to talk about all today is redox equations, okay, and what redox is. So I'm going to start off by just giving you a bit of a background about redox. Hopefully you've done this in year 11, but just in case you haven't, a quick refresher. So redox stands for reduction and oxidation put together. Okay, I've deliberately done that not in a red colour, so it's not actually referring to red at all, but that's reduction, that's oxidation. Okay, so when we're talking about redox, we need to understand what it actually is. Okay, so firstly we're going to talk about oxidation. Oxidation is a loss of electrons, an increase in oxidation number, or a gain of hydrogen. Okay, any of those three things, if that occurs, that tells us that we've got oxidation occurring. Okay, reduction, conversely, is just the flip of it. So if we look at reduction, reduction is a gain of electrons, a decrease in oxidation number, and a loss of hydrogen. Now most of the time we don't really talk about hydrogen in terms of reduction, we're generally always talking about electrons or oxidation number. Okay, we can talk about oxygen in there as well, and it's pretty straightforward. Oxidation is a gain of oxygen, but we're going to just be focusing on a gain of electrons or a transfer of electrons and oxidation numbers. Okay, so the easy way to remember these two is by using this first little an acronym called oil rig. Okay, so oil rig stands for oxidation is a loss of electrons, reduction is a gain of electrons. Okay, so that's the first thing you need to remember. Oil rig, burn it into your memory, and that just relates to electrons. If we want to focus on the decrease in or increase in oxidation number, remember your vowels and your consonants. Okay, so your vowels, oxidation is an increase in oxidation number. For your consonants, reduction is a and that should be a decrease. Sorry, not a G. That's a D. Okay, reduction. All right, is a decrease in oxidation number. So your consonants go together, your vowels go together. Okay. So what I'm going to quickly go through is just firstly how we work out our oxidation numbers. Okay, and there's a couple of things you need to be aware of, but most of the time it's normally just the charge. Okay, so if we start with something really simple like water, H2O, okay, overall the charge of this molecule is 0. Okay, now in here we know we've got an oxygen that has a -2 charge. Okay, so we've got an oxygen that's made up, that's a 2- charge. Okay, we've got a hydrogen in here which is a 1+ charge. Okay, so our oxidation numbers in this case are actually identical to our charges. So our oxidation number up here is -2, our oxidation number up here is +1. Notice the difference of how we write charges and oxidation numbers. So charges is the number, then the sign. Okay, oxidation number is the sign and then the number. So oxygen here is an oxidation number of -2, hydrogen has an oxidation number of +1. Okay, and you'll notice that when we add up our oxidation numbers, it equals the overall charge of our molecule. So that one's really straightforward. So I'm going to start going through some of the, I guess, the rules that we're looking at. Okay, first off, if you have a atom or atoms by themselves, okay, that have no charge. So I'm looking at things like if you've got a magnesium atom like that, or if you've got chlorine, Cl2, okay, or let's go with nitrogen, N2, okay. The charge on all of these is 0. So the oxidation numbers on each of these are 0. Okay? So if it's by itself, okay, either lots of them by together or just one by itself, the oxidation number is 0, always. Okay? If it's combined, if it's an ion just by itself, so I'm talking about Cl-, Mg2+, okay, let's go with N3-, okay, so I'll just put the 1 in there to make it easy for you. The oxidation number is equal to the charge, okay, so here the oxidation number is -1, here it's +2, here it's -3, okay, so that oxidation number always matches up to the charge on the monatomic ion, so one that's by itself. So when you start combining them, that you start to get a little bit different, so I'll show you some of those combination ones. Alright, so and I've already shown you water, where they all add up, but I'm going to show you some that have charges. So I'm going to start off with a very common one, MnO4-. This is permanganate, okay, has a really beautiful magenta colour, okay, so that sort of colour there, that's your permanganate, Okay, and we're going to use this in titrations as a bit of an endpoint. It goes from colourless, all right, to a pale pink when we're going through and doing it. Okay, so in here we have our oxygens, and we know that our oxygen is made up of -2. All right, normally oxygen is always -2 except when it's with hydrogen peroxide. Okay, so here the oxidation number for oxygen here is -2. So our oxidation numbers have to balance up. 4 lots of -2 gives us -8 overall, and our charge up here is -1. So we want to get to -8 to -1. To do that, you have to add 7. So the oxidation number of our manganese up here is +7. Okay. If we look at another one, dichromate, Cr2O7 2-. Okay. Oxygen is always -2. So 7 lots of -2 gives you -14. We want to get to -2. Okay. To go from -14 to -2, we need to add 12. Okay. But we've got 2 chromiums here. So 2 lots of 6 gives us our +12. So our chromium is +6. Our oxygen is -2. Okay. So that's a couple. They're probably the 2 of the most common ones that you need to look at. Okay, so I'll just show you maybe 2 others quickly as well. So one of them I told you about that's really important that you remember is hydrogen peroxide, H2O2. Okay, now hydrogen in this case, all right, is a +1. Hydrogen is always going to be +1 unless it's with a metal, and I'll show you that one next. So because our hydrogen is +1 here, our oxygen must be -1. That is the only time oxygen's -1. Every other time it's -2. Now the only time that hydrogen is not a +1 is if we have something like this, NaH, so sodium hydride. Okay, sodium can only be +1. It's in group 1 of the periodic table. Metals will always pretty much have their oxidation number equal to their normal charge. So in this case, the hydrogen needs to be -1. So if it's a hydrogen with a metal, it's going to be -1. Otherwise, it's +1. Oxygen is always -2 unless it's with hydrogen, in which case it's -1 there. Okay. So, best thing for you to do is practice some of those, writing out your oxidation numbers. So you might want to try some of these, Cl2O7 2-, work out what your oxidation number of the chlorine is there, work out what your oxidation of the nitrogen is in that one, look at your oxidation number of your sulfur in that one, look at your oxidation of your sulfur in that one. Okay, see if you can work out each of those oxidation numbers. All right, give them a try. And what you should hopefully end up with, all right, is 7 lots of -2 is -14. You need to add 12. Chlorines there are +6. That's like your dichromate. Okay. Your nitrogen in this one are +5. Your sulfurs in this one are +4. Your sulfur in this one is +6. All right. Have a go. See if you can match up and get those exact same numbers. So what I want to show you is redox equations, and we normally call these half equations, and the reason for that is we're actually looking at half of an equation. Okay, what we don't often see when we're writing out a full balanced equation is where the electrons go. Now, not every equation is a redox reaction. Okay, and we can determine if it's a redox reaction if there is a transfer of electrons. Okay, so that's what determines a redox reaction. So when we're doing our redox equations, okay, there's 3 main steps. Now, we'll actually point out this red bit down the bottom I put here. Make sure your other atoms balance first. And so I'll go through that as I actually go through some equations, and hopefully it'll make sense. So I'm just going to start off with a couple of basic ones to begin with. So I'm going to take hydrogen peroxide, H2O2, and I'm going to have that going just over to water, H2O. Okay, so first off, what we do is we look at our metal atoms. There are none, so we can go on to the next step. We balance our oxygens with water. So we've got 2 oxygens here, only 1 oxygen here. Okay, so we can add another water. We can have plus H2O, but obviously it would make more sense to go 2 H2O out the front. Then we go on to balancing up our hydrogen atoms. We've got 2 here, we've got 4 here, so we need 2 hydrogen atoms on this side. Now we look at the overall charge. Okay, here we've got overall 2+, so that's a 2+ charge over here, and over here we have no charge. Now the only way we can balance charge is with electrons, okay, and you can only add electrons, which are a negative charge, so we need 2 negative over on this side to balance up and make that 0. so 2 electrons over on that side, and that gives us our overall half equation, H2O2 plus 2H plus 2E minus 2H2O. Okay, now what we can look at here is that this is a gain of electrons. Okay, we're adding in 2 electrons here, so there's a gain of electrons here. And as we know from our oil rig, okay, reduction is gain, so this is a case of reduction. So that means that this H2O2 is actually an oxidizing agent. So what that means is oxidizing agents are themselves reduced. This H2O2 will oxidize something else. So if you actually think about it as well, H2O2 is going to H2O. It loses an oxygen, it's giving that oxygen. So that's another way of thinking about oxidation. So I'm going to move on to another one. Okay, this time we'll look at H2O2, but we'll look at it forming oxygen gas. Okay, so this is the other way that hydrogen peroxide can be involved in a redox reaction. So we start off no metal atoms, move on to step 2, balance our oxygens, they're already balanced. So we move on to balancing our hydrogens. There's 2 on this side, so we need 2 on this side here. Okay, we balance our charge, there's an overall 0 charge on this side, there's a 2 plus charge on this side, so we need to add in 2 electrons over on this side. Okay, that balances up our charge, it balances our atoms. This is a case now of a loss of electrons, because the hydrogen peroxide over here has now lost 2 electrons, so we've lost electrons. Alright, oxidation is a loss, so this is an example of oxidation, which means that the hydrogen peroxide in this case is acting as a reducing agent. So it will reduce something else. Okay, let's look at another one. So now I'm going to look at dichromate, Cr2O72 minus, and this forms chromium ions, Cr3+. It's going to make that a bit smaller because I need a bit more room. Okay, so this is now a good example where you look at balancing your metal atoms first. Over here we've got 2 chromiums, so here we need 2 chromiums on this side. That will balance those up. Now we look at balancing our oxygens. 7 oxygens here, so we need 7 waters over on this side. Okay, on to the next step, which is balancing our hydrogens. 7 times 2 is 14 hydrogens, so we need 14 lots of hydrogen on this side. Now we look at balancing our charge. This is where it gets a little bit more tricky on something like this, so you've got to make sure you check everything. We've got 2 minus there, and we've got 14 plus there. Okay, we've got 2 lots of 3 plus there, so we've actually got 6 plus charge over on that side, or a total charge over there. 2 minus plus 14 gives us a total of plus 12, and we've got 6 plus over here. So to go from that to that, we need 6 negatives, don't we? So over here we have 6 electrons, right, on this side. Hopefully by now you'll be able to start having a look at this and starting to recognize the patterns. In this case, what we've actually got here is a gain of electrons. Okay, so that's oxidation, reduction I should say. Gain of electrons is reduction, oil rig, which means that the dichromate is an oxidizing agent. And you really need to get your head around that, remembering that oxidizing agents are reduced. But again, look at it that the dichromate Cr2O7 is now Cr3+, it's lost oxygen, it's given that to something else, it's oxidized it. Alright, I'll do 2 more. So I'm going to look at sulfur dioxide, okay, and I'm going to look at forming the sulfate ion, SO4, 2 minus. Okay, sulfurs are balanced here, we don't need to worry about that. Okay, so we just start moving on to our oxygens. 2 oxygens here, 4 here, so we need 2 lots of water on this side. Now we balance up our hydrogens. 2 lots of 2 is 4 hydrogens here, so we need 4 H plus on this side. Balance up our charge. Overall here we've got nothing. Here we've got a 2 minus and a 4 plus. Okay, 2 minus 4, so that gives us negative. So that gives us positive 2 overall. Okay, so we need 2 electrons here to balance that out. This is an example of a loss of electrons, which is oxidation. Okay, so the sulfur dioxide in this case is a reducing agent. Okay, last one I'm going to show you is permanganate. Okay, MnO4 minus, and that goes to manganese ions, Mn2 plus. Okay, really nice redox reaction, this one, because there's a really nice colour change involved with a deep purple colour for the permanganate and the manganese. So you'll see this used quite a lot in titration, so it's really useful to use this. Okay, so what we've got here, manganese, both balanced, so we move on to our oxygens. We've got 4 oxygens here, so we need 4 waters on this side. 4 times 2 is 8 hydrogens, 8H plus. Okay, and now we need to start looking at our charge. Right, we've got -1 here, +8 there. Okay, -1 plus 8 gives us +7 in total. Right, and a 2 plus here. So to go from 7 to 2, alright, we need 5 minus 5 on there, so 5 electrons up here. Okay, this is an example of a loss of electrons. Loss of electrons is reduction. Okay, so our permanganate over here is an oxidizing agent. Okay, so I've given you a number of different examples there. Okay, hopefully you can start going through and practicing these. All of these are what we've done is balanced with hydrogen ions H+, and that's normally what happens in redox reactions. But I want to show you one example where occasionally things will happen under alkaline or basic conditions. You obviously can't balance with H+ under basic conditions, so the steps are a little bit more involved, but I want to take you through and show you one of those now. Okay, so what I'm going to show you is a redox reaction now done under alkaline conditions. So remember, alkaline means water-soluble base, so what we're actually using here instead of H+ to balance is hydroxide ions of OH-. So I'm going to show you, I'm going to take this species, CrOH6 with a 3- charge, and we're going to make that over into CrO4 with a 2- charge. So what we're going to do is we're going to actually go through this and do it as a normal redox equation first, but then we're going to get rid of the H+ ions to make it alkaline, and I'll show you what I mean. So start off 1 chromium, so we follow that step, that's done. Balance up our oxygens. We've got 6 oxygens here, 4 here, so we need to add 2 waters over on this side. Still exactly the same as we're doing normally. Balance up your hydrogens. 6 here, okay, 4 here, so we need 2 hydrogens. Now we balance up our charge. 3- on this side, 2- and 2+ on that side, that cancels out to 0, so we need to balance up 3-, so we get 3 electrons over here. So that's fine for a half equation if this was done under acidic conditions, but we've got a hydroxide here. This is clearly going to be an alkaline solution. So what you do in this scenario is you start adding in hydroxide ions to balance out or get rid of the hydrogen ions, okay? And remember, whenever you add something to one side, you've got to add it to the other. So we've got 2 H+ over here. We want to have 2 hydroxide ions over here. They actually will cancel each other out, but we need to add our 2 hydroxide ions over on this side, okay? Now, if you think about it, H+ and OH-, alright, if you add them together, you will actually end up with water. So we've got 2 of them, so we're going to end up with another 2 waters. So now what we can do is we can start to rewrite our equation. CrOH6 with a 3- plus 2 lots of hydroxide ions gives us CrO4 2-, 2 4 water molecules and 3 electrons. Okay? And what we've actually done is remove the H+. We've made this now an alkaline redox equation. If you have a look, all the atoms balance, charge is balanced, 3- and 2- is 5-, 2- and 3- is 5-, and so what we've done is we've turned our half equation in acidic conditions into a half equation under alkaline conditions. So all you've got to do is actually just add your hydroxide ions to get rid of your H+, and you're fine. Alright, hope that helps. Best thing to do with redox reactions is practice, practice, practice. Let me know if there's any issues. Thanks guys. See ya.